We now turn to a perspective from industry, and this will be talked about by David Guy from Imperial.
Oh. That's like magic. Right. So thank you. I'm David Guy. I'm a professor at Imperial College in Materials and a Royal Society Industry Fellow. So I should give a hat tip to EPSRC there with Rolls-Royce. And probably in the industry space, we're a bit further back, but we've been thinking quite hard about what the opportunities are and what going essentially to shorter pulses faster would enable us to do. So as a case study example, familiar to me, for the significance of industry in the UK economy, this is Rolls-Royce, which is something like 0.6% of UK total employment is derived from this company and their product, which are the engines for twin-aisle aircraft. And in a good year, when you don't have a pandemic, then we're talking about something like 13 billion, 16 billion in revenue. When everybody stops flying, that's a big problem, of course. And this is also from a emissions and sustainability perspective. This is about civil aerospace, about 3.5% of total warming, so CO2 equivalent, because it's a bigger problem if you're emitting it at altitude. And we generally want to go home again afterwards when we've gone flying. And the great thing about air transport is that it's exceedingly safe, which is important. So I'm going to talk about some failures in a minute. So I just want to get my apologies in first. Generally speaking, we go home again afterwards, right? But the reason we do that is that we look at the failures, right, and worry about those. So a few years ago, I did a couple of experiments at LCLS, where we started to think about, what would this enable us to see that we can't see normally with synchrotrons. So just as an example of why that's interesting, this is a synchrotron experiment from early in my career, where there was a science paper announcing a new material with some amazing properties and postulating a mechanism by which it derived those properties. And we went and did a synchrotron experiment where we showed that actually it was conventional superelasticity due to a phase transformation that was stress induced. And then if you came and that went away when you unloaded it, and the people who had developed the material hadn't happened to look in the right direction, and so hadn't been able to observe that transition and had misattributed it. So that is, in situ experiments let you see things that you didn't expect, right? Which is sort of obvious, but it kind of always needs saying. It's an evergreen thing to be able to say to people. So here's an example from our first experiment at LCLS. This is zirconium. It's a low temperature, low pressure HCP arrangement. High temperatures, then you have a BCC arrangement. But if you go to high pressures, then you can transform to this omega phase here, which is generally a nuisance phase. It embrittles titanium and zirconium alloys. But this sort of high pressure phase can be useful in some engineering objects in order to give you a compression boost and things like that. Now, the pathway to go between these different structures we usually measure by static experiments, or we can model by DFT. But the question then is, well, if you go fast, is it the same? And it turns out that it may not be. So this is the sort of thing we're doing. So we're hitting a foil in this case with an optical probe. It has to be a foil because the beam is so low energy. And then we rattle a shockwave through it and see the new phase appearing. So you get a very, very fuzzy ring there. And all of your HCP rings have gone away. And this is we've seen some of these segmented detectors earlier from CXI, and a bit where we blew it up with a laser and so on. And they're generally, you are really pushing the detector technology with these experiments, would be the observation. And then what we do is two things. You can, this is a given pressure you're applying, a given energy from the laser, higher and higher again. These are two of the HCP peaks. And as you put the pressure through, you can see the peak move, and you can relate that to a stress. You go to a higher pressure, you can see a new peak appear, which is your omega phase, and then completely transform. Now, in terms of the pathway, if you then look at the variation intensity around the ring, you can infer what the orientation relationship between the original and new product phases are, which tells you about the sort of pathway that you must be going through. And it turns out that when you go and look in the shock experiment, you get a different orientation relationship to that you do from a quasi-static experiment in a diamond anvil cell. And so that then leads you to say, okay, well, we must be doing a shuffle this way, as viewed here, which would be involve larger atomic motions, but more direct, so it can happen quicker. That's our sort of hypothesis. And so you can see things you wouldn't otherwise expect to see. Moving on, this is work with Justin Walker and Andy Higginbotham and so et al. On copper, where we did a sort of parasitic experiment on the back of their experiment, which was to go and look at sacs. So again, you've got a laser pulse, which is compressing the sample. You're then probing that with your X-ray beam and then looking at the strains on the wax, on your X-ray, on your conventional diffraction detector, and then having another one a few meters away to look at small angle X-ray scattering and to look at void growth. So the sort of thing here is as you shock your foil, then you initially are compressing it, and that compression wave is moving through the material. It takes a while for the material at the back to realize that something is going on. And it gets a rather rude surprise, right? Then when you get to full compression, you then bounce off the back surface and go into tension, and that then starts to result in void nucleation and failure. And of course, the surface here is in plane stress, so the void nucleation happens a little bit into the interior of the material. So from a diffraction perspective, what that looks like is a new peak appearing, which is just the compressed part. The strains are so large that it actually appears as a new peak. When you fully compress, that new peak has grown. It's broad, of course, there's lots of dislocations in there and lots of defects. And then as you expand, you end up back with your original peak, albeit massively damaged. When you look at the SAC signal, then it's dramatic. I'd never seen so much SAC signal before in my career. I usually look at nanoprecipitates at sort of 0.1 volume percent, voids that scatter enormously at, percent, all the way up to 25% was a huge revelation. It was like, will we see anything? Oh, yeah. It was dramatic experiment. SACs, you quite often worry, am I modeling when I'm modeling it, am I going to be imagining it in little bumps on here? No. In this case, the amount of signal you're getting is quite large. So as you go through full compression, what happens actually is you compress some initial voids that were there in the foil, because this is a sputtered foil. And it turns out that when people say, oh, it's fully dense, it's not. Then you expand the voids up and you see them come through, and you can then fit that in your SACs. You can see the volume fraction comes down from initial volume fraction of 0.4%, and then you have to change the scale to the right-hand axis as you go through the release and void growth phase and watch them grow, and you can even get the diameter of them, and it's just, it's amazing. Then Andy comes along and does the MD modeling and infers what the strain rate must have been and the spall strength, and we come to the conclusion that actually this was the highest spall strength and strain rate experiment MD had ever done, which was pleasing. So that was just an example of where you can go and where you can find things that you weren't expecting. So spalling in shocks had been sort of talked about for decades, of course, but nobody had really been observing them. So it was really, really pleasing to be able to come along with SACs and observe that. Thinking about more engineering type applications, then this is more sort of having some think between the group about what sort of things we could do. It's very common in industry to use converging, diverging nozzles to do things like thermal spray, to spray ceramics or coatings onto turbine blades, for example. And there you have a supersonic jet through which you are dropping your material, which you're sputtering onto your surface. You want something better than a 10 micron resolution. You may be solidifying those particles in flight if you're making a metal powder, or you may be splatting it onto the surface. It's such a joyful technical term, splatting. And then looking at them solidify and looking at the phases that form. And they're very complex structures, typically in the in the actual ceramic coating business. And so you want something like a nanosecond time resolution, which is on the edge of synchrotrons, but you don't really have the flux. You can only image. So we'll talk about that a little bit more in additive. Another example is particle stick bounce, which is kind of interesting. A couple of years ago, Rolls-Royce had a multi-billion-dollar problem in the Trent 1000, where it turned out, there are many dimensions to the problem in nickel superalloys and in corrosion and so on. But it's a low temperature corrosion problem at sort of 400 degrees C, which hadn't been seen before in nickel alloys. And it turned out that one of the issues was that the air system, the cooling air system, was delivering cooling air much quicker to the blade than had been done in previous engine designs. There's a change in the way the ducts work. And so the sulfate sort of particles that you have, imagine flying over Saudi Arabia, lots of sort of talcum powder type stuff, then you're delivering that wetter, not fully dried out. And so your particles can stick rather than bounce effectively. And that's very hypothesis driven, because you can't then observe it afterwards. They all fall off, but it suddenly corrodes. So if you want to observe them stick rather than bounce, well, again, you're at sort of 1500 meters a second, they're 10 micron particles. If you want to be able to observe those on the surface, do some chemistry, actually doing chemistry, doing Zanes, yeah, we're down below a nanosecond again. And we want the flux because we have a photon hungry application. Two more examples. Scientific instruments, I just point out that a lot of the things that we do quite routinely in things like atom probe microscopy and femtosecond machining, we don't have a great amount of insight into what's actually happening when we're doing those processes. And they're very fast. And it might be nice to have more than models. Similarly, in jet engines, we do things like laser shock peening to manage the stresses on the surface. We put a laser beam down, have an ablative coating that generates a plasma that generates a shock. Those are optimized as processes by looking afterwards. They're probably far too, apply far too much strain to the sample, put far too much damage in, and we could do better if we could optimize them by measuring what's going on in a transient state. Last one be, this is Peter Lee's work on additive manufacturing. And you have a lot of processes going on in additive manufacturing. You're generating a keyhole of a plasma. You have then solidification at the back surface. You have particles going off. And the keyhole is really good for bouncing around the laser light inside of it and improving your efficiency. You have cracking at the back end. You have precipitation. And most of these processes, it would be nice to be able to observe rather than just look afterwards. Then the keyhole collapse process, we're just about being able to image now, just as imaging from absorption by taking a sort of 1 millimeter thick slice off. This is aluminium, but we'd like to do it in nickel superalloys and in titanium, right? But we don't have enough energy. We don't have enough photons. Even this is the upgrade program at ESOF. We don't have enough photons to do more than image, to do any diffraction or anything else. As an example of the sort of thing that lets you realize, this is, I think, is really cool. Most metal powders are atomized in argon and have porosity inside of them. And when you melt them, this is in a conduction mode, actually, rather than keyhole mode, then all of those argon pores can go and agglomerate together and generate a large pore, which is then a crack, right? Which makes the product effectively not very good in fatigue, which is why we don't tend to use these in rotating parts if we can avoid it. And if you could modify the Marangoni flow, then you could, to stop this happening and pop the bubbles, you wouldn't have the problem. Because it's very hard to get rid of the argon porosity in the original powder particles. So, but nobody had ever even imagined that this might be going on before Peter did the observation. So if you could, the hypothesis would then be that if we could then do diffraction and so on at the back of a melt pool, we would find other things that it would be useful for us to know. So there is engineering application at short time scales, which is quite critical industrially, but it often takes academics to help translate, to conceive of how doing in situ experiments might help, which is a bit like neutrons and synchrotrons were in the 90s when I was an undergraduate. And that's the difference in the fields. We've made a start with a few experiments, but it's still, from an engineering perspective, quite early in time. And really what the opportunities look like, they're sort of megahertz imaging at fluxes and pulse directions faster, more brilliant than synchrotrons. Not right down at the attoseconds, but at picoseconds. And laser shock peening looks like a nice application to me. In terms of what we're needing, really, you know, most of the synchrotron work that I've done in my career is at 60 plus kV. You know, if you're thinking about a millimeter of uranium, well, you want 120 kV plus, really, right? But even nickel, you know, you need 60 to really get very much through. And the other thing that's different is to say, well, we're wanting to go and do industrial processes at the beamline, or approximants to industrial processes at the beamline. And that, if you think about what the inside of somewhere like MEC looks like, yeah, tricky to go and put a Condi nozzle in there, right? So that's one of the big challenges with doing these sorts of experiments that are industrial relevant. Thank you very much.